14.3, which is entitled The Elastic Force, also known as Hooke's Law. If you take a look at the book, the first thing that it has you do is to examine two spring scales. So this first one, the green one, is a 5 Newton spring scale, which means it only can hold a weight up to 5 newtons. The second one is a 20 Newton spring scale, so it can hold a weight of up to 20 newtons. Now, on the back, or on the opposite side, I should say, on this side of the spring scale, if you can see it, you can see the N for newtons. On the other side is the mass. It's a unit for mass. It's in grams. And so the first blue dot question asks you how the same device can measure both weight, which is a force, and mass in grams. And if you think back to the formula for weight, the formula for weight has a mass component to it. It's the gravitational constant, 9.8 times mass. So because weight and mass are proportional to each other, we can accommodate both of those scales on the exact same device, just by basically applying the proportionality constant. So these spring scales measure both newtons, which is the weight or the force due to gravity, and grams, the mass. Now, one of the things or the main thing we're really looking at in this lab, the purpose is to look at how the weight of the object in newtons is related to the stretch of the spring. So let's talk about elastic force a little bit. Elastic force is basically any force that you can apply to a spring that will cause the spring to either stretch or compress. Now, it's not just springs, it's anything elastic, like rubber bands you can apply elastic force to, bungee cords, shocks in your car shocks have elastic force. So elastic force, again, is anything that you can apply a pressure or a force to that causes the spring or the rubber band or the bungee cord or the car shocks to stretch and compress, depending on which way you're applying the force. The other component that is required for an object to be considered to be elastic is the fact that once we stretch it or compress it, it will go back to its original shape. So there are certain objects, like I could take a ruler and I could bend it, maybe break it in half, right? If I took this and I bent it to break it in half, I can't get it back to its original shape. And actually that's not really stretching or compressing. So you can't really take most objects and manipulate them in a way that they'll go back to their original shape. So this, again, elastic force has to do with applying a force that causes a spring or something like it, like a rubber band or a bungee cord or car shocks, to stretch and then resume its original position, or compress, if you think about pushing it together, applying a force that way, and then it would resume its original shape as well. So elastic force is what we're looking at. We're looking at the relationship between the elastic force, so the weight of the object, and the stretch of the spring. That's what we're looking at. So basically what I had my students do is take any object and hang it on the spring scale. Well, first we need to zero it out. So the first thing we would do to zero out the spring scale, how good you can see it, okay. So, I'm sitting it a little closer so you can see this. If you can see in the top here, there's this disc that sits at the top. And I know it's hard to read the numbers on it right now, but when you hold them up close to your face, you'll be able to see it. There's this round disc. So we want the 0 newtons to line up with the top of the disc. So we want to hold it by this top little handle and see where the top of that disc is lined up. If it's not lined up at the 0, then holding it from here, you would turn this little screw at the top to adjust it so that the top of that disc is in line with the 0. That's when you know that it's calibrated properly or zeroed out. So once we do that, then we would take an object and hang it from the spring scale and kind of let it even out, and then measure how many newtons of force or the weight of the object, and we would record that. Okay. Now, we want to be able to measure the stretch of the spring in centimeters. If we tried to do it this way, because remember, we're looking at the relationship between the weight of the object, how many newtons of force it is, and how much that spring stretches. So trying to measure with a centimeter ruler here is probably really kind of tedious and hard to do accurately. So what we would do is we would look at the mass, and this one is, I'm sorry, the force or the weight, which is in newtons. This one is 0.7. This one's 0.7 newtons. So then what I would have my students do is I gave them these little photocopies that look like a spring scale. Let's get a little closer. See if I can, if that'll help. Okay. So the best thing to do is to then say, okay, let me find 0.7 on the photocopy of the spring scale. By the way, this is to scale, not to have a play on words here, but this is drawn to scale so that we can write down, we can mark the number of newtons that the object weighed, and then we can take the centimeter ruler and measure the centimeters of stretch. So here's what that would look like. If this is, it's 1, it's 0.5, 0.6, 0.7. So 0.7 newtons. So if you can see that on here, 0.7 newtons is the weight of the object, which was my scissors. I weighed those. Now what I would do is I would take my centimeter ruler and I would line up, see if I can do this backwards, the 0 on the centimeter ruler with the 0 on the Newton scale. And I would measure how many centimeters the spring had to stretch to accommodate 0.7 newtons of weight. And that's what we're looking at, the relationship between the weight of the object and how many centimeters that the spring stretched. I'm trying to say that slowly because that's easy to, it's a tongue twister. So 0.7 newtons of force, or weight, and how does that correlate with the number of centimeters that the scale had to stretch? Okay. In this case, this 0.7 newtons of force would equate to 0.7 centimeters of stretch on the 5 Newton scale. That's about how that would correlate. So I had my students write it down like this. So 0.7 newtons of force equates with 0.7 centimeters of stretch. Again, that's what we're looking for, is what is this relationship? That's the whole purpose of the lab. What is this relationship between the force and the stretch? Then I had my students use the 20 Newton scale. And again, we zero it out the same way. This one's not even close. Let me work on this one a second. We want to get it to zero out, so the top of that disc needs to be in line with the 0 on the scale. And because this can accommodate more weight, we should take, measure something a little bit heavier. I should have planned ahead of time what I was going to use. Let's see, what can I, oh, I know. Let me grab this bucket. Okay, here we go. You guys can see me. Let me focus again. Okay, so now I have the 20 Newton scale. I've got my bucket of goodies. And my bucket of goodies has a weight of, oh gosh. By the way, when you're looking at these 20 Newton scales, the scale is set up completely different than the 5 Newton scale. That one's easy to read. It's important that you look at how this is set up so you can read it ahead of time so that you're not standing here trying to figure it out in the middle of it. Let's see, that's 4, that's 6, that's 5 in the middle. I'm going to call that 5.5 newtons. So 5.5 newtons, and really I probably could find something a little bit heavier, but we're going to go with that for now. So then I take the picture of my 20 Newton scale, again drawn to scale, and I'm going to mark the weight of my object in newtons. Right about here, 5.5, right in the middle. 5.5 newtons. And then again, I'm going to take the centimeter end of my ruler, or the centimeter side, and I'm going to line up the 0 on the centimeter ruler with the 0 on the Newton scale and measure how many centimeters the spring had to stretch to accommodate 5.5 newtons of force. So in this case, let's see. Let's look at my hair's all up in there. Let me move over to the side. Let's see. That is 1.3 centimeters. Okay. So on my 20 Newton scale, 5.5 newtons of force turns out to stretch that spring 1.3 centimeters. Okay, now what I would do is have the entire class gather their data. So we'd have a data table for all the objects measured on the 5 Newton scale and a data table for all the objects measured on the 20 Newton scale. And then we would graph the data. Again, if we want to look at a relationship between two variables, a graph is the best way to visually see how that data should play out. So if we graph the data of the 5 Newton scale and the 20 Newton scale, here's basically what it would look like. See if I can hold this up without losing all of my random papers that are in here. Let's see. 65. Okay. So let's take a look at the 5 Newton scale on top. Let me see if I can get this to focus. Hopefully. Okay. Well, the top one is a picture of the 5 Newton scale. Across the bottom, we have stretch in centimeters, so 1 to 6 centimeters of stretch. Up the left-hand side, which is hard to see on the y-axis, is the force in newtons, and it goes up to, this one's up to 6, even though the 5 Newton scale can only accommodate 5 newtons of force, but it still goes up to 6. There you go. When we plot that, you can clearly see that it is a direct relationship. As the force increases, so does the amount of stretch. And it's a basic 1-to-1 ratio. If you look at the slope of the line, you can figure out what their proportion is. If you figure out the slope of the line, at the top it says that it's 0.96. It's about 1-to-1. So 1 Newton of force equates with about 1 centimeter of stretch for the 5 Newton scale only. A couple of things that you need to know about proportionalities that will come up later on in this chapter. We know this is a proportionality for 2 reasons. First of all, it starts at the origin, which means if there are 0 newtons of force, then there is 0 stretch. So the first data point is 0, 0. That is one characteristic of a proportion. It has to start at the origin. And from there, it's basically linear. It's a straight line. There's a constant slope. In this case, the slope is about 1. It's just a teensy bit less than 1. Now, you'll notice the same thing for the 20 Newton scale. We graphed stretch on the x-axis and we graphed force on the y-axis. It's still proportional. It's linear. It still starts at 0, 0 and goes in a linear fashion up from there. The only difference between the 20 Newton graph and the 5 Newton graph is the slope of the line, which kind of makes sense. If you look at the way that's calculated at the top, the slope of the line is slightly less than 4. Really, it should be about 4, which means for every 4 newtons of force, the spring will stretch 1 centimeter. Now, if we kind of think about that for a second, let's think about how that plays out. If you think about a 5 Newton scale, it requires a certain spring to be able to accommodate 5 newtons of force. A 20 Newton scale is going to need more, it's going to need a different spring to be able to accommodate more force. So it's basically a tighter spring. If you have a chance, you should feel these because it's very clear that that spring is a little bit tighter because it has to be able to accommodate more weight. This scale is about 4 times this scale, right? This is 5 newtons and this is 20 newtons. 5 times 4 is 20. So this one's about 4 times this scale. And then if you look at their proportionality constants, the proportionality constant for the graph of the 5 Newton scale is about 1. The proportionality constant for the 20 Newton scale is about 4. 4 times the scale for the 5 Newton scale. So I kind of found that interesting when we were looking at the numbers. Both spring scales show a direct proportion, which means the strength of the force, or the weight, is directly proportional to the stretch of the spring. And that is what Hooke's law tells us, that the spring will stretch in direct proportion to the weight that it has to maintain. And that's Hooke's law. Let's see if there's any other blue dots that I missed. I think my conversation covered the last 2 blue dots, although not directly. And I believe that you will have some resources to help you out with those as well. But that's the gist of 14.3. It's very straightforward, very direct, kind of fun. I like the spring scales. So if you have any questions, please feel free to let me or Miss Kirk know. And there's my reload. Bye.